Ladies and gentlemen, good afternoon. Welcome to the fifth session of the Thematic Symposium of TC3, Fracture and Fatigue Failure of Engineering Materials and Structures. It's a pleasure for me to chair this session. My name is Camilla Ronchei from the University of Parma, and my colleagues are Daniela Scorza and Andrea Zanichelli, also from the University of Parma. Before starting this session, I would like to remember you that for each speaker, a slot of 15 minutes is scheduled, including questions and comments. So please be respectful of the scheduled time. Now we can move to the first presentation. The speaker is my colleague Andrea Zanichelli. And the title of the talk is Microstructural, Mechanical and Fracture Behavior of a GR-reinforced mortar at different curing times.
Well, thank you, Camilla, for your kind introduction. Well, ladies and gentlemen, good afternoon. My name is Andrea Zanichelli, and I am a research fellow from the University of Parma in Italy. Sorry, I asked for the... Yes, thank you. Well, before starting the presentation, I really would like to thank my co-authors from the same university. And so, well, here is the goal of the present work, that is to experimentally investigate the mechanical properties in terms of both flexural strength and compressive strength and fracture toughness of cement-based specimens reinforced with graphene oxide nanoplates, as well as their microstructural features. So my presentation consists of the following sections. After a brief introduction related to cement-based materials reinforced with nanomaterials, I will describe the experimental campaign carried out at the University of Parma on a cement-based composite reinforced with GO nanosheets, and then I will focus on the results obtained during this experimental campaign, and finally some conclusions will be drawn. So, well, cement-based materials, that is cement and mortar, are the most used construction materials all over the world, and this is mainly due to their low production cost, of course, and the high versatility in response to the design requirements. But despite the many desirable features, the main disadvantages of such materials are represented by the low crack resistance capability, that is to say a low fracture toughness, and to the presence of intrinsic defects. So improving the mechanical properties and reducing the size and number of defects may result in the increase in the performance and durability of such materials. And an effective way to enhance the mechanical performance of such materials is obtained by adding nanomaterials into the cement-based matrix. And among nanomaterials, graphite or graphene-derived materials, such as GO, represent reinforcing bidimensional nanofillers in the form of nanoplates, which are able to improve the microscopic properties of cementitious materials due to their excellent physical and chemical properties. Well, as a matter of fact, according to the technical literature, GO nanoplates can regulate the microstructure of the hydration crystals during the cement hydration phase, and so leading to an increase in the mechanical strength and in the fracture toughness of GO-reinforced cementitious composites. Now, let me describe to you the experimental campaign we carried out at the testing laboratory of the University of Parma. So, in particular, the raw materials employed for the preparation of the GO-reinforced mortar specimen were the Portland cement, a standard silica sand, a polycarboxylate superplasticizer that is named PC, and the graphite powder. Then the GO in aqueous solution was obtained from the oxidation of the graphite powder by means of the Brodie's method. And then the mixture proportions employed to cast the specimens for the GO-reinforced specimens are listed in the first line of, well, of the first table, this here, by weight of cement. Then we also casted the plain mortar specimens that are the PM specimens with the same proportions of cement, sand, water, and PC. And note that the proportions shown in the first table are those used to cast the specimens to be subjected to the mechanical and refractor tests, whereas the sand was not considered for casting the specimens for microstructural analysis. Both GeoReinforced specimens and plain mortar specimens named GeoStar and PM star, since the presence of sand could make difficult the interpretation of the result from a mineralogical point of view. So, as far as the mechanical tests are concerned, both flexural tests, compression tests, and fracture toughness tests have been carried out for both plain mortar specimens and GeoReinforced specimens at different curing times. And in particular, for each curing time considered, 3 prismatic specimens with the nominal geometrical sizes shown here have been subjected to 3-point bending tests in order to determine the flexural strength. Then the 6 half prismatic specimens resulting after performing the flexural tests were subjected to compression tests in order to determine the compressive strength. And moreover, 4 prismatic specimens with the nominal geometrical sizes shown here in the top and with a notch in the lower part of the middle cross section have been subjected to 3-point bending tests in order to determine both the elastic modulus and the fracture toughness by means of the modified 2-parameter model. Well, such a model that has been proposed by Vantadori and co-workers allows us to take into account the possible crack deflection during the stable crack propagation phase, even in the case of a remote pure mode 1 loading applied to the specimen. So, as you can see in the graph here on the bottom right part of the slide, where it is represented a typical load crack mouth opening displacement graph according to the modified 2-parameter model. Each specimen is monotonically loaded up to the peak load under crack mouth opening displacement control. Then the specimen is, when it reaches a load value of about 95% of the peak load, the specimen is fully unloaded, and then it is finally reloaded again under crack mouth opening displacement control up to the final failure of the specimen itself. Then, as far as the microstructural analysis is concerned, small cubic molds were filled with fresh slurry without sand. That is, as I said before, the PM star and the Geo star specimens. Then they were cured in laboratory for 24 hours, demolded and submerged in water for the different curing times we have examined. And then for each curing time considered, 1 specimen per type was dried for 1 hour at a temperature of 30 degrees, and then divided into 2 portions, one to be subjected to the SEM ADS analysis, and the other one instead milled for the XRD analysis. In this slide, a summary of all the specimens we considered for both microstructural analysis and mechanical characterization, it is flexural compression and fracture test, is shown as a function of the curing times we have considered, that is to say from 3 days up to 120 days. And now let's have a look to the results we have obtained. As far as the microstructural analysis, no differences in terms of crystalline morphologies have been observed between the PM star and the Geo star specimens for all the curing times considered. As you can see, there is an example of an XRD pattern on the top right part of the slide for both PM star and Geo star specimen. Then in the lower part of the slide, the XRD phases quantified are plotted against the curing time. So the more significant results have been obtained for the amorphous phase, that is the CSH, and for the Etringite, that is AFT. And in particular, the amorphous phase content increases for both specimen types, but the increase is more remarkable for the Geo star specimens, and also the values obtained for Geo star specimens are always greater than the corresponding ones for PM star specimens. And also, if we look at the CSH content for PM star specimens, we can see that it increases up to 14 days, and then it remains quite stable up to 120 days. Then the AFT content increases for the PM star specimens, where a completely different trend. So it decreases for the GO star specimens. Whereas for the other crystalline phases, as well as for the main cementitious phases, no significant remarks can be done. So at least for the microstructural analysis, we can conclude that the GO addition mainly results in the variation of two hydration products content, that is the increase of the amorphous phase and the decrease of the ethylene. Relatively to the mechanical tests, here are shown the results in terms of flexural strength and compressive strength. On the left, we have the flexural strength that increases up to 90 days of curing for both PM specimens and GO specimens, and then it remains stable up to 120 days of curing for both of them, with higher values for each curing time registered for the GO specimens. Whereas on the right side of the slide, we have the compressive strength results that in particular, the compressive strength increases up to 28 days of curing for both specimen types, and then it remains quite stable up to 120 days of curing. And in this case, comparable results have been obtained for the two types of specimen, especially in the stable part that is from 28 and 120 days of curing. And finally, the results that we obtained after performing the fracture tests. In the higher part of the slide, we have the load crack mouth opening displacement curves that we obtained testing the both PM specimens and GO specimens at 90 days of curing. As you can see, the curves are quite similar to each other, both in the inner elastic stage and in the final softening branch, even if slightly higher values have been obtained for the GO specimens in terms of peak load. And then by employing the modified two-parameter model, as I said before, we computed both the elastic modulus and the fracture toughness. So the elastic modulus, for the elastic modulus, we obtained an almost constant values independently of the specimen type and on the curing time considered. Whereas in terms of fracture toughness, we obtain an increased up to 90 days of curing for both specimen types, with the values of the GO specimens always higher than that of the PM ones. And as you can see, this trend is completely similar to the trend we obtained for the flexural strength, even we consider the less curing times. So we can assume that at 90 days of curing, also in terms of fracture toughness, we have reached a sort of stable values for both PM specimens and GO specimens. So, and now let us move to the conclusions. In the present research work, a cement-based materials reinforced with the 0.05% of GO nanosheets has been experimentally investigated at different curing times to determine the microstructural properties, the mechanical strength, and the fracture toughness. So as far as the microstructural analysis is concerned, the addition of GO mainly results in the variation of two hydration products content, that is the increase of the amorphous phase and the decrease in the ethylene phase content. And whereas as far as the mechanical characterization is concerned, the flexural strength and the fracture toughness of the GO specimens have been found to be always greater than those of the PM ones for all the curing times analyzed, and then to stabilize after 90 days of curing. So we can conclude that the improvement that we observed in terms of mechanical properties can be related to the variation of the amorphous phase and of the ethylene contents. In particular, the increase of the amorphous phase promotes in the GO-reinforced specimens an interfacial bonding within the cement matrix and a greater amount of small pores with respect to the PM specimens. Whereas the beneficial role of a low AFT content could be explained by considering the growing mechanism of such crystals that growing fast may exert an expansive force within the matrix, leading to cracking. And so a low AFT content would lead to a less damaged cement matrix. So thank you for your kind attention.